Dr. from Anveshana Academy, Bangalore, India. Dear students, in the previous class we discussed about what is Carnot engine, how it works, what are the important components of Carnot engine, okay, what are the important process it is having, how it works, what is adiabatic expansion, adiabatic compression, and what is isothermal expansion and compression. In detail we have discussed in the previous class. Now I will move towards next topic. Next topic is efficiency of an Carnot engine. Okay, so dear students, our next topic is efficiency of an Carnot engine. Okay, so what is this efficiency of Carnot engine that you can see? A heat engine used to produce maximum work transfer from a given positive heat transfer. The measure of success is called thermal efficiency of an engine, and it is denoted by neta. That means what actually is telling now, he has considered a heat engine. Okay, he supplied heat to the engine with the help of a heat source, and he's actually theoretically is telling that engine is doing maximum work with supplied heat. Then how much amount of work is done with supplied heat? He measured with the help of a parameter. That parameter he called as a thermal efficiency, and that thermal efficiency is represented by what? Neta. So what actually he has done? Carnot is a scientist. Okay, he's invented this engine, and it's a theoretically he assumed, but practically it is not possible. So he's considered an engine. So, and he has considered two sources here now. One is heat source, and it works at temperature T1. Okay, and it is going to supply heat. That heat is represented as a Q1, and the heat is going to, he consider one more source, that is sink or waste heat sink we can call, or low temperature region we can call. It works at temperature T2, and the heat rejected to the heat sink is represented as a Q2. Okay, with the help of heat supplied and heat rejected, he calculated the work done. So work done can be calculated as capital W is equal to amount of heat supplied, that is Q1, minus amount of heat rejected, that is Q2. So therefore W is equal to Q1 minus Q2, where W is work done by the engine, Q1 is the heat supplied to the engine, whereas Q2 is heat rejected from the engine. With the help of this data, what we can do? We can calculate the efficiency. So one thing. So now we already know, dear students, I am telling work done here now. How to calculate this work done, the Q1 minus Q2? Yes, it is calculated based upon the first law of thermodynamics. First law of thermodynamics is what it tells: amount of work done is equal to amount of heat supplied, or amount of heat supplied is equal to amount of work done here. So capital W is equal to Q, net heat you can consider. How to calculate the net heat? Amount of heat supplied minus amount of heat rejected. Whatever the net heat is there, right, that much work is done. So this equation we got it from the first law of thermodynamics, that is capital W is equal to Q1 minus Q2. That is the amount of work done by the engine. Like that he has represented in a engine. With the help of this data, he calculated in a efficiency. What is that efficiency? We already know, dear students. Efficiency is equal to what we can say generally, work output divided by the heat input. So how to calculate the efficiency of this engine? So efficiency is equal to work output or work input, or output to the input. What is the output here we are getting from the engine? That is work. Then what you are giving as an input? That is heat. That heat supplied you are giving, that heat supplied is represented as a Q1. So what is W? That W you already know here, dear students. W is equal to Q1 minus Q2. So I will write it W is equal to Q1 minus Q2 divided by Q1. So Q1 minus Q2 divided by Q1. What we can do then? Later efficiency is equal to 1 minus Q2 divided by Q1. So efficiency is equal to 1 minus Q2 divided by Q1, where W is the net work transfer by the engine. Q1 is the amount of heat supplied to the engine, whereas Q2 is equal to heat rejected by the engine. Okay, so now this can efficiency of the Carnot engine with the help of heat data. I can express the equation like that. If we are having temperature data, with help of the temperature data also we can calculate the efficiency of the Carnot engine like this. That is neta C, efficiency of Carnot engine is equal to 1 minus T2 by T1, where T2 is the temperature of the cold reservoir. So you can see cold reservoir is nothing but what, sink. Okay, and T1 is the temperature of the hot reservoir, that is hot source. So therefore Carnot efficiency I can express in terms of heat data, that is 1 minus Q2 divided by Q1, or else temperature data, efficiency of Carnot engine is equal to 1 minus T2 divided by T1. This is what efficiency of an engine. So with the help of this equation, he calculated the efficiency and he is assuming that it is 100%. But but he has calculated that he is, and somewhere else he is telling there is absolute temperature is 0. That means what? There is no heat, there is no temperature difference, temperature is 0. That means what, there is no heat transfer to the sink, but whatever heat is supplied to the engine, right, it will utilize the complete heat and it is going to do work. But he assumed, but practically it is not at all possible. I mean, if you are supplying 100 joules of energy as an input, if that means he is getting 100 joules of work output, but it is practically it is not at all possible. 100 divided by 100, it is 1, again 100%. But he assumed Carnot engine is in a theoretical ideal thermodynamic cycle. So but it's a benchmark, but it's practically it is not possible. Hence what we can say, note, heat engine can be 100% efficient. He calculated the efficiency of the engine, that he is telling that 100% efficient, but some heat engine always lost to the low temperature sink, but heat engine practically they are going to reject the heat actually. So this is what efficiency of the Carnot engine. Okay, then how we derive this equation? Okay, with the help of this equation he has calculated the efficiency of the engine and is shown that it is 100% efficient, but practically it is not possible. That's fine. Then how we derive this equation, that's also important. The derivation is very important, and you may get the derivation for 6 to 8 marks. What's that derivation? That will move towards that derivation now. Okay, so now I will move towards derivation of efficiency of a Carnot engine. So as I told dear students, how many processes are there? 4 processes. Okay, the first process is process A, you can call, that is process 1 to 2. 1 to 2 is nothing but what I told. This I will take a PV diagram and I will take a schematic diagram of working model. So this point we can call it as a TDC, this point we can call it as a BDC. Here is the complete, it is insulated, and one end is open. Sometimes it acts as an insulation, sometimes it acts as a thermal conductor. Okay, based upon our requirement, that we will see. Okay, the process 1 to 2 already we studied. Process 1 to 2 is what? Isothermal expansion. When the piston is, that means the piston is going to move from TDC to BDC, where what happens? The volume is going to increase from V1 to V2. The volume is going to increase from V1 to V2. At point 1 temperature is T1, at point 2 temperature is T2. As I told, the heat, that means what, you are going to supply heat, right? The piston is getting expanded from point 1 to point 2, as I told. That means what, the heat is supplied at constant temperature. Due to this heat supply, what happens? The piston is going to expand. That process we can call it as a isothermal expansion process. That means what, you are going to supply heat at a constant temperature. The supplied heat is represented as a Q1. The temperature is represented as a T1. Okay, whereas volume is going to increase. Okay, that we can see when the piston moved from TDC to BDC. That means what, you are going to supply certain amount of heat, right? That amount of heat supplied is represented as a QS. Some authors they will take QS, some authors they will take Q1. You can take Q1 or QS, it's up to you. Here I will take QS now. Both are same, so you can see now some notation. So Qs is equal to Q1. Some authors they will take heat supplied, some authors they will take Q1. Some authors they will take Qr is equal to heat rejection. Some authors they will take it as a Q2. It's up to you. Okay, the both notation I'm using here for my convenient now. So heat supplied, because we know already isothermal expansion work. So we know that expansion work is what? P1 V1 ln of V2 by V1. This equation we know already. Work done for an expansion process, isothermal expansion process. This is a work done equation. According to first law of thermodynamics, we know that amount of heat supplied is equal to amount of work done. So therefore heat supplied is equal to work done at the isothermal process is Qs is equal to P1 V1 ln of V2 by V1. This is the equation. Okay, so now this equation where what actually I told you, now I'm using in a gas, right? That what type of gas I'm using? Ideal gas or perfect gas I'm using. Ideal gas or perfect gas I'm using. If I'm using perfect gas, that gas obeys the ideal gas law. That is what ideal gas equation. What is that ideal gas equation? PV is equal to mRT. So this is the common equation. That the equation I'm going to modify as per my requirement. So P1 V1 is there. So that P1 V1 is equal to what I can write? mRT1. M and R are the constants. So I will keep it as it is. Whereas temperature is a variable, I will keep it T here as a T1. So P1 V1 is equal to mR T1. So therefore I will modify this equation. So therefore Qs is equal to what you can write now? Qs is equal to P1 V1 is what? mRT1, mRT1 ln of V2 by V1. So this I will call it as a equation number 1. This I will call it as a equation number 1. So what is heat supplied? Heat supplied is equal to work done, that too for isothermal expansion, that is P1 V1 ln of V2 by V1. Whereas P1 V1 is, we know that is ideal gas equation, PV is equal to mRT, where M and R are the constant, I will keep it as it is. Where T is the variable, I will write it T as a T1. So P1 V1 is equal to mRT1. The same thing, this is the value of P1 V1 I will substitute here now. So then what will happen? Heat supplied is equal to Qs is equal to mRT1 into ln of V2 by V1. That I will call it as equation number 1. So process 1 to 2 is over. Now I will move towards process 1 to 2 is over, right? So now I will move towards process 2 to 3. What is process 2 to 3? So you are going to stop the heat supplied. You are going to put a adiabatic wall, but heat transfer is there. Heat is there inside the gas. Still piston is moving. That we can call it as a expansion process, but there is no heat transfer from system to the surrounding. That we can call it as a adiabatic expansion. If there is no heat transfer, then what we can write? We can write Q equal to 0. So when there is a hot body is removed, the hot body is removed and insulatory cap is kept, then what happens now? So then adiabatically the volume is going to change from V2 to V3. So initially it is V2, V2 is less. Now again expansion is taking place, hence V2 change to V3. That means what? V2 V3, the volume of the piston at point 3 is increased compared to V2. Okay, and temperature is going to falls from T2 to T3. So temperature is, as the volume is going to increase, the temperature is going to drop it here now. Okay, so now when the piston reaches BDC, that means what? Volume change from V2 to V3, as well as temperature also changes from T2 to T3, but there is no heat transfer at all. So therefore what I can do? The heat transfer I can write it here Q equal to 0, but the variations in the temperature, that I can express in terms of what? Because temperature as well as volume, they are going to vary. That I can express in terms of an equation, that is T2, this is T2 divided by T3 equal to V3 by V2 to the power of what? Gamma minus 1. So what I can write it here now? So T2, see here now, T2 divided by T3, vice versa, V3 divided by V2 to the power of what? Gamma minus 1. This is temperature variations at a particular process, that is 2 to 3, that is adiabatic expansion. So this I will call it as a equation number 2. Equation number 2. Okay, so now this is what expansion is done now. Now I will move towards next process, compression. Okay, one expansion, there are two, isothermal expansion as well as adiabatic expansion. That's fine. Now I will move towards 3 to 4, 4 to 1. Now I will move to 3 to 4. That means what I will try to compress. I will remove this insulating cap. I will open this and I'm going to attach a sink here now. Then what happens? And compression I will try to start from 3 to 4. That means what compression you are doing, but the heat is getting transferred from cylinder to the sink at constant temperature. That heat rejection is represented as a Q2 or QR. The constant heat is rejected at constant temperature, that is represented as a Q2 or QR. That we can call it as a isothermal compression. So isothermal compression, but the heat is getting rejected from system to the surrounding. That is very important, you know. In the first process, isothermal expansions, you are adding heat to get the work done from the system, but here in the second you are rejecting heat. So the heat rejection is represented as a Q2. From 2 3 to 4, 3 to, your piston is from here 3 to 4, assume that 3 to 4 you are going to compress it, but the heat is getting rejected. 3 to 4 we can call it isothermal expansion, but heat is getting rejected into the sink, that is represented as a Q2. Again, at what temperature? The temperature remains constant. During process 3 to 4, heat is getting rejected at a constant temperature T2. That process we can call it as a isothermal compression. Isothermal compression, and temperature remain constant as I told. Okay, that is T3 equal to T4. T3 is equal to T4. That is what? Lowest temperature. Here you can see at highest point T1 is equal to T2. This is highest temperature, whereas T3 is equal to T3 is equal to T4. That is the lowest temperature. Okay, fine. Now adiabatic compression, from 3 to 4 you moved. Okay, fine. Now immediately what I will do, I will remove the heat sinks. I will put again insulating cap. The completely become insulated, but still piston is getting compressed. That we can call it as a compression process, but heat is not at all transferring. That we can call it as a adiabatic compression. So 4 to 1, the piston is going to compress from, it will move from 4 to 1, but heat is not at all transferring, but the compression process is happening. That we can call it as a adiabatic compression. If it is adiabatic compression, heat is not at all transferring, that means what? Heat is 0. Okay, fine. Now adiabatic expansion is done. Now I will move towards third one, 3 to 4. I will try to write the equations that we can see here now. What is third one? Process 3 to 4, that is isothermal compression. So what actually happening now? Volume is getting decreased, that we can see, dear students. Now in the compression, expansion volume is getting increased. When during compression 3 to 4, right, volume is here, but when it is moving from 3 to 4, the volume is getting decreased. If the piston still moved from 4 to 1, again still the volume is going to decrease. That means what? Volume is changing from V3 to V4, means the volume is getting decreased. Okay, the volume is changed from V3 to V4 when the piston moved from, what is the point? BDC to TDC. So piston is now moving from BDC to TDC. The volume is going to change V3 to V4, that is decreasing. Then that amount of heat rejected, that we can write it in terms of, again as I told, heat supplied is equal to work done. Then work done for at isothermal compression, we are having an equation, that is QR is equal to P3 V3 ln V3 by V4, where P3 V3, again PV is equal to MRT, ideal gas law. Okay, the whole process were same gas, right? That means what? That gas following the gas law or ideal gas law, that is PV is equal to MRT. So PV, that how I can write it now? MRT 3 ln of V3 by V4, that I will call it as equation number 2. That I will call it as equation number 3. Okay, fine. Now last process is what? Adiabatic compression. Last process is, dear students, you can say adiabatic compression, but there is no heat transfer at all. But there is no heat transfer. Again, volume is going to change from V4 to V1. That means it is getting decreased, and temperature is also going to vary from T4 to T1. But the piston is moving towards TDC. That's very important here now. So therefore, what I can write it now? The heat transfer during compression at adiabatic process is 0, but temperature variation I can write it in terms of an equation, that is T4 by T1 is equal to V1 by V4 to the power of gamma minus 1. That I will call it as equation number 4. So now I written the equations for all the processes. That I means what? Carnot has written equations for the different processes. Based upon the equations of this process, he calculated the efficiency. How he has calculated efficiency? We know already efficiency of an engine is equal to work done divided by heat supplied. How to calculate the work done? We know already. Work done, efficiency of Carnot engine, generally work done divided by heat supplied. Heat supplied, you can take it QS. So what is work done? That also you know. Work done is equal to what? Amount of heat supplied divided minus amount of heat rejected divided by amount of heat supplied. The same thing I have written it here now. So amount of heat supplied minus amount of heat rejected divided by heat supplied. That we can write it here like QS minus QR divided by QS. Dear students, already you know the equations. Okay, you written the efficiency equation, but what is the value of QS? You already know it somewhere here now. What is the value of QS that you already calculated? You have to put it now. What is the equation? QS is equal to, now equation number 1, QS is equal to MRT1 ln of V2 by V1. Okay, so now QS is done. What is QR? Somewhere else we have written QR also. What is the QR? You can see here now. QR is equal to heat rejection is equal to equation number 3, MRT3 ln of V3 by V4. Now substitute the value of QS and QR in efficiency equation. Then here QS is also same again. So I will try to put the values now. So that you can modify this equation. Even you can rewrite this equation, right? Efficiency is equal to, so 1 minus, because in the denominator in numerator side QS is there, QS minus QR is there, denominator QS is there. This I can write it like this, 1 minus QR divided by QS. The same thing I have written it here now, 1 minus QR divided by QS. What is the value of QR? You already know. So that is what, MRT3 ln of V3 by V4. Then what is QS value? That is MRT1 ln of V2 by V1. This you can call as equation number 5. But then one condition you have to remember, dear students, during for a Carnot cycle, the compression ratio is nothing but what? Here V3 to V4. That is nothing but a compression ratio. We can call compression ratio V3 by V4 is equal to expansion ratio. What is expansion ratio? That is V2 divided by V1. Both will be remain same. That is the one condition you have to remember. So compression ratio of a Carnot cycle is equal to expansion ratio. That is what? A compression ratio is 3 to 4. Expansion ratio V2 1. Both are remain same. Now equation you can see here, dear students. V3 by V4 is there. What is V3 by V4? That is V2 by V1. Substitute V2 by V1. So then here also V2 by V1 is there. Just a minute. Here also V2 by V1 is there. Here also V2 by V1 is there. Get cancelled. Again gas is a constant. Gas is gets constant. M is constant. M is constant. Then only thing is what is left out here? Land already gets cancelled. Then only thing is left out what? T3 and T1. So therefore what I can write? Efficiency of an engine is equal to 1 minus T3 divided by T1. What is T3 here now? T3 is the lowest temperature. Then what is T1? T1 is the highest temperature. So then what I can write now? This equation I can rewrite like this also. Efficiency of Carnot engine is equal to 1 minus TL divided by TH. What is TL here now? Temperature of lowest point, or sink we can call, that is T3. Then whereas TH is nothing but what? Highest temperature of the reservoir. So therefore what I can write it here now, where TL is equal to T3 or T4. TL is equal to what? T3 or T4, lowest temperature, where TH is what? Highest temperature, that is constant temperature, that is T1 is equal to T2. So where T1 is equal to T2 is TH, T3 is equal to T4 is a TL. So therefore efficiency, final equation of what I can write, efficiency of a Carnot cycle, some authors they will write like this, some authors they will take neta C is equal to 1 minus lowest temperature divided by highest temperature. This is the efficiency of a Carnot engine. Okay, so I hope you understood the derivation and what is Carnot efficiency. Okay, dear students, herewith I request you, please do subscribe my channel, do comment, okay, like and share my videos to your friends also. Please do support. Thank you.